Okay, good morning. My name is Terry Quinn. I'm the director at the Institute for Geophysics and also a professor in the Department of Geological Sciences. So I'm quite pleased today to be the moderator of this panel, which is really a list of rock stars. So on the sheet of white paper that you all have are the list of accomplishments of everyone. I'm not going to read them off, but just let me introduce the panel to you first. The first panelist is our keynote speaker, Mark Zoback from Stanford University. He's a member of the National Academy of Science. Our next panelist, as we go over here, is Sergey Fromel. Sergey is the Pratt Professor in Geophysics. He's a joint appointment in the department in the Bureau of Economic Geology. Liz Logan. Liz just finished her PhD this fall and is now a postdoc at ISIS, and she's working with Omar Gattas on things. So we're going to get the perspective of a student who just finished for that. And then we have Don Blankenship, who's a senior research scientist at the Institute for Geophysics, and then Laura Wallace, who's a research scientist at the Institute for Geophysics. So we had a great start from the geology panel. Hopefully we'll continue on that way. I certainly expect we will, with a wonderful talk by Mark Zoback. Mark?
Well, thank you. As the title of this slide suggests, I had a little bit of trouble kind of getting my head around what I was going to talk about today. I got advice that I should be telling the Jackson School what it should be doing for the next 10 years. I got some advice that as a senior distinguished, which basically is a polite way of saying old, scientist, I should sort of reflect personally on geophysics. And I've sort of taken this advice and not taken the advice. So what I really want to kind of address is why geophysics is needed to save the world. This is my shot after I have 3 degrees in geophysics, the first of which is from the University of Arizona. I'll come back to that later. And I've been a geophysics professor for 31 years. So I have some perspective on the issue, and this is probably the only opportunity I'm going to have. So I'm going to try to tell you why geophysics is needed to save the world. And, you know, I have just tremendous respect for the Jackson School, both the Geoscience Department, the Bureau, and the Institute. And you'll play a big part of that, and it's important. Now at Stanford, you know, as we talk about our own program in earth energy and environmental science, you know, we organize around some big themes that people can relate to. Obviously, securing energy for the future is a major global challenge. Understanding and dealing with climate issues is a major challenge. Natural hazards of many types is a third. And of course, food and water security. And so, you know, we try to keep our eye on the big picture, the things that are really important to society. Now, having been in the school for 31 years as a professor, 4 years as a graduate student, I sort of got used to our old name, which was the Stanford School of Earth Sciences. Kind of said it all as far as I was concerned. But the issue that came up at the end of the last panel has sort of geology, not, you know, is it kind of a worn out word? Is it a word that reflects on science that used to be important? Really troubled some people, and we went through a whole process of renaming the school, and this is where we wound up. It's almost unpronounceable. Practice on your own. It takes too long, you know, to actually say what the organizational unit I belong to, but it does encompass what we do, and so it has some practical utility. But as the process was playing itself out, I had an idea, and I've got 50 colleagues, and then there's the dean and the provost and the president, and absolutely no one else liked this idea, because what I wanted to call it was the School of Geophysics. Because geophysics is needed to save the world. There's actually another reason, and it actually has to do with what came up also in the previous panel, and that's the evolution of the geological sciences. it's changed dramatically. It's not recognized by the public, but when we say geological sciences, whether we're talking about geology or geophysics or whatever, we're talking about a discipline that's very, very different than the discipline was when we were in school. And that reflects the changing landscape of the problems that we have to help solve. And that's greatly to our credit. And it is unfortunate that people might associate the geological sciences with science that had been important in the past, because if there's no other purpose of my talk, and I think George Davis's talk, is that the role we have to play in addressing the problems of the future. And I'm going to use the American Geophysical Union as an example of that very point. So I just survived the December meeting. Many of you were no doubt there, and if you're here today, you survived as well. It's gotten to be kind of a marathon, and if you run a marathon, you know that the idea is to get to the finish line, alive, right? And getting to the Friday night of AGU week is usually my goal. It's simply a remarkable event. Now, the American Geophysical Union represents 25 highly diverse disciplinary areas. So everyone who goes knows a lot about something, right? And yet, it's the integration of those 25 disciplines that makes the AGU experience so wonderful, and especially wonderful for young people, and of such interest to the public. And so now, if you go to the AGU channel, you'll find talks organized around climate, around Earth discovery, around extreme events, weather events, and natural hazards of all types, about natural resources, and that's kind of new to the AGU. In the past, it was sort of more of an academic organization, about planetary discovery, and about science and society. And so, this community of 25 groups of disciplinary experts are not, promoting their disciplines so much as joining together to address these large global societal problems using their disciplinary expertise as a tool. So for the young people in the audience, and I'm going to assume there are young people and there's old people in the audience, and you can put yourself in either category. For the young people in the audience, this also has been a transformational part of our disciplines, and it was good to hear it discussed during the last panel, because in the past, all that was expected of us is that we achieve disciplinary expertise. And I was talking to a prospective student at the AGU, and he had just spoken to another professor, and he said, another professor to another institution, and a person I knew and respected, and it was a great school, and he said his advice was, working in earth science was like digging a hole, and you just keep digging. And what he meant was, to succeed, you had to be an expert in a disciplinary area, and you had to become more and more and more expert. And I don't agree with that. You have to be an expert in a disciplinary area for sure, but what you really need to do is understand what the problems are and apply that disciplinary expertise in a coherent way. And that's what I find the AGU to be so exciting about is the quality of the science, but the application of that science to important problems. There were 24,000 of my closest friends at the meeting. We've not only run out of poster space, we're even running out of floor space now, and it's really not clear what's going to happen in the future. Now, I do want to point out that George Davis referred to Robert Grudem and had some really profound philosophical remarks. I'm going to refer to Yogi Berra, who says, nobody goes there anymore, it's too crowded. And the AGU is going to maybe reach this point, but it's really a victim of its own success. And if again, for the young people, if you haven't been to an AGU, go. It'll be a life-changing experience. So, doesn't the School of Geophysics make perfect sense? The other thing I was asked to comment on, is to make a few personal observations. Now, this picture is almost exactly 40 years old and represents my first position as a postdoctoral scholar. I became a driller's assistant. And I had done my master's degree in sort of theoretical seismology. I'd done my PhD working in a laboratory doing sort of rock mechanics and rock deformation. And I had a troubling thought, and that is, does any of this actually have anything to do with the real world? And I realized that the application of rock mechanics and seismology to real-world problems revolved around understanding the forces that were in the earth. And I recognized, with advice from a number of senior colleagues, that those forces were really unimportant at the Earth's surface and highly affected by weathering, topography, all sorts of secondary effects. And if I wanted to understand the stress field, I had to make measurements at depth. And to make measurements at depth in a robust way, it had to be through using drill holes. And so I had to learn how to drill holes. And so my first job was as a driller's assistant. Now, the young people in the audience will know that both the glasses and the beard are back in fashion. Anyway, and so is wearing hard hats, so I have learned a few things. But literally, this is an acoustic scanning device, which is now in widespread use in the oil and gas industry, but was an experimental device, and so we had to build the equipment to actually look at the rocks. So we were trying to avoid fractures, pre-existing fractures, and then I got interested in the fractures, but we were avoiding fractures to use hydraulic fracturing as a technology for measuring stress. And little did I know 40 years later that hydraulic fracturing would be on everybody's lips and would be the great pejorative. You do fracking, and yes, proudly. And anyway, it was a great grounding. And what I realize now, because people have pointed it out to me, is that it was sort of a step toward doing multidisciplinary science. And I want to come back to that, and George also referred to it. So with respect to this, this first challenge of trying to understand what the forces in the Earth's crust are and how they affect geologic processes, something I started working on 45 years ago and continue to work on today, we look at it at the scale of plates, and this is work I started with Mark Zoback, and in 1980 we published our first stress map of the central and eastern United States and showed that there was tremendous coherence in stress orientation and stress magnitude. Now again, for the young people, I did this as a sort of a second project, and she did it as a second project. We kind of worked, it was before we had kids, we worked on it in the evening, on weekends, and everybody told us it couldn't be done. Well, what more incentive did we need than that to prove everybody wrong? And so we made these maps, and later led to a world stress map effort that Mary Lou led. And our goal was to try to use the knowledge of the forces in the crust to better understand plate driving forces and to better understand intraplate seismicity. Now we understand, plate tectonics taught us about earthquakes on plate boundaries, but intraplate earthquakes were quite mysterious. Where did the forces come from? Were there localized forces every place there were localized groups of earthquakes? And we actually found it was the opposite. We found the forces reflect plate driving processes, and that we found that the intraplate earthquakes were simply responding to those regional forces. This map was published a couple years ago by a student and I, and it kind of updated the database and showed something that Mary Lou and I pointed to in our 1980 paper, but it was extremely speculative because the data were simply so poor, and that is that there seems to be a systematic increase in the nature of the compressive stress, how compressive the stress field is, as you go more or less from the mid-continent to the northeastern US and southeastern Canada. And we felt that in 2012 it was sufficiently well defined now by the data that we could actually sort of contour it in this with these background colors. And this actually poses a fundamental constraint on one of the big mysteries of plate driving forces, because you have to balance the forces, and gradients of stress tell you a lot about tractions at greater depth that we'll never be able to access directly. Little did we know, as we were sort of looking at these sort of big picture grand challenge questions, at least they were grand challenges to us, did it come to pass that, of course, the stress field guides what direction horizontal wells are drilled. The stress field controls the nature of induced seismicity, whether it occurs or not, which faults it occurs on, and most of the faults in the Earth's crust are dead, and happily so. And issues like the feasibility of large-scale CO2 sequestration. And so there's a real linkage between fundamental science and applied science. And I try to never think about that distinction. It just sort of works itself out. If you're working on the right things and you're asking the right questions, maybe it's going to be, have application to real world problems. Maybe it won't, but you'll be making a contribution. You'll be moving knowledge forward. Now, when I was a graduate student, I heard a talk by a very distinguished scientist at the Geological Survey, Art Lockenbrook, and he was an expert in the heat flow coming from the Earth. And my undergraduate training at the University of Arizona was sort of explaining geophysical anomalies, which is sort of classical geophysical training, right? A seismic event is an anomaly, a wave bouncing or refracting along some interface. A gravity anomaly, a magnetic anomaly, right? Why is the magnetic field, the gravitational field, different in one place than another? And Art's talk was on an anomaly he did not see. And I thought, what? And what he was saying is, if the laws that govern earthquakes and deformation in intraplate areas, which we have spent a fair amount of time confirming, if those laws were applicable to plate boundaries like the San Andreas Fault, the motion of the fault should generate a lot of heat. In fact, it's just like rubbing your hands together. The heat generated is the stress times the velocity. And we know how fast the San Andreas Fault was moving. If we put the standard laws into that fault, there should have been a big thermal anomaly. There should have been hot springs and other sources of evidence for heat coming from the San Andreas Fault, and there was none. So now I found myself as a young scientist trying to digest this, because what it really meant was that all the laws that govern faulting in an intraplate environment, based on laboratory measurements and sort of theories of geomechanics, did not apply to the faults we cared about the most, the big faults, the plate boundary faults, the faults that generated big and often devastating earthquakes. And so this really bothered me. And it also bothered me that it didn't bother everybody. I mean, some people were just as happy to figure, well, the rock mechanics was just fine, this heat flow data is just crap, forget about it. And the other people said, the heat flow data, is important, it's telling us something, so let's just ignore all that laboratory rock mechanics and all this other stuff. The world is the world, and let's just accept that. So this question of why plate bounding faults have low frictional strength just haunted me, for years, until we decided to do something about it. And that led to the SAFOD project, the San Andreas Fault Observatory at Depth. So we wrote a proposal, myself, Steve Hickman, and Bill Ellsworth, and submitted it to the National Science Foundation, and they said they liked it, but there were some other things that they'd like to see improved. And so we modified the proposal and sent it back. And this time they liked it a lot. They convened a high-level panel of very distinguished scientists, and they affirmed the validity of our the goals and the project and the necessity for the project. But it cost $20 million. And there wasn't $20 million, to spare. And it would be, just unreasonable to take $20 million out of the core program and then give it to one project. That's not a viable solution. So a very clever associate director of the National Science Foundation, Bob Carell, turned a problem into an opportunity. And he said, well, let's do something. And he basically was the stimulus for what became known as EarthScope. And EarthScope was a $200 million project, and the great majority of the money was spent on seismology and geodesy, and about 10% of the money was spent by us, and that was just fine. We were all extremely pleased, and 3 large communities of the earth sciences got to participate in EarthScope, and EarthScope remains an extremely important program. And so, it took this institutional leadership to take, well, how am I going to fund this proposal? I can't just ignore it. It's too highly reviewed, but I can't fund it either. And they made EarthScope, which is a tremendous advance for all of the solid earth sciences. So in SAFOD, we wanted to drill into the San Andreas Fault and address a lot of long-standing questions. So we had to drill into the fault, we had to sample the rocks and fluids, we actually, we had to conduct science, we had to operate a geophysical observatory, and it's not just any hole. The rocks have been mechanically shattered, chemically altered by tens to hundreds of thousands of earthquakes, and in fact was moving during the process of us drilling through it. So we reached out to private industry, and we had a remarkable group of technical panels helping us, advising us about how to do this. And it was still a bit of a booger. It was hard. We did it in 3 stages, 2004, 2005, and 2007. In 2005, we successfully drilled through the fault and logged it, collected cuttings, gases, and that was great. But we really had to collect core samples. If we hadn't collected core samples, I think the great majority of people would have considered the project a failure, despite the other things that we had accomplished. And so now I'm 16 years into this project, and it was 9 weeks of hell. Drilling projects can go south sometimes, and just getting these core samples out, as I sometimes say, the San Andreas Fault decided to fight back, and it was really hard. Sleepless nights. I'm only 35 years old. Where do you think all this gray hair came from? Anyway, we finally succeeded, and the cores were absolutely spectacular. No one had ever anticipated what the San Andreas Fault would look like. And we could actually hold it in our hands, we could send it to laboratories around the world, and we could literally engage hundreds of scientists to ask long-standing questions. And now we know why the San Andreas Fault has low frictional strength. It's an odd clay mineral called, it's a smectite mineral, and it's not a commonly occurring saponite. This is why I'm not a mineralogist, by the way. It was saponite, which is a daughter product of serpentine, and in fact it had been recognized earlier by Bill Dickinson and others that the creeping section of the San Andreas Fault seemed to be geologic controlled by serpentine in contact with the fault, and when serpentine was not in contact with the fault was stuck and produced big earthquakes. And so he pointed that out decades earlier, but no one knew what the actual link was until we could actually get the core samples out, see the mineralogy, test the rocks, and as the saponite was more and more concentrated in a localized zone, the fault became weaker and weaker, and that's what localized the deformation. So we now know, what the fault composition is and the behavior of the fault. We can now do laboratory simulations using realistic materials and so on. So, it was absolutely the result of multidisciplinary science. It was absolutely the result of a group of people identifying what a societal goal was, and that is, not to just leave these questions unanswered or leave them for someone else to answer, but to engage them. And it was the ability of the National Science Foundation and the vision of the National Science Foundation to fund something that was expensive, something that was difficult, and something that might not succeed. And those are all the things that make Silicon Valley go when you stop to think about it. And it's when government organizations can be entrepreneurial in that way, we all benefit. So SAFOD wrapped up in 2007, and I was looking for something else to take over my life. There's no point in sleeping. It's a character flaw that many of you have. And it suddenly dawned on me that the energy world was changing. And some of you already knew this, but in around 2005, unconventionals started to come on the scene. And what I did is I started to go to meetings of petroleum engineers. And someone said, well, how did you learn this stuff? And I said, well, it's not so hard. All you have to do is stop what you're doing and immerse yourself in the subject matter. So I went to meetings, and I wasn't giving talks, I was listening. And then I went to another meeting, and I listened again. And suddenly, I could see, one is the enormous importance of this revolution that was taking place. And second, I could see a role for the disciplinary expertise I had in addressing problems, within that revolution. And, I drank the Kool-Aid, and Scott and many of you are heavily engaged in this, but it's really been a truly remarkable ability, and it's a wonderful thing about being a professor, is to sort of go off in this new direction. Not completely new. I'd worked, with the oil and gas industry through my whole career, but now I was sort of going all in. And the more I've gone on all in, the more I realized it was the right thing to do for me at that time. And I like to show this slide to students because in 2050, the world is going to be a crowded place. So we're going to have something like 9 to 10 billion people. We're going to have to be providing twice as much energy as we do today. And we need to do it in a way that sustains economic growth, that reduces environmental impacts, that respects national security issues, and conforms to societal norms. So for the young people in the audience, if the enormity of this task doesn't scare you, you're really not paying attention. This is one of the hardest things modern society has to do, and we're all going to do it together, or we're all not going to do it together, and the consequences will be extremely severe. And what's at the heart of it, of all this, is that this rock could power the world. We all saw this cover of Time a few years ago, and these are very complicated rocks. And to give credit to my geologic foundation, I was here in the spring giving a departmental seminar on petroleum engineering, and the subtitle of the talk was "The Rocks Matter," and they really do. And I think the next suite of challenges for unconventional resource development is to make the progress we've made in operational efficiency, make the equivalent progress in understanding these reservoirs so we can improve these rather dismal recovery factors, and which changes not only the supply side of the picture, but the economics. And 5% recovery out of tight oil reservoirs is simply not good enough. But there's another side of it, and that's the public concern about the environmental impacts and the tremendous pushback. And so those of us who are, at a certain point in our careers where we have the ability to influence public opinion and how the sort of the multiple sides of this issue present themselves, are very heavily involved in trying to understand and to address the environmental impacts of the development and to bring society along. And they're not on, this is Texas. And, the oil industry is part of the culture, part of the history. But outside of places where the oil industry has long been present, there's suspicion, there's distrust, and there's concern about real issues. And it's that latter part that's important. And we have to address community issues. We have to address atmospheric issues. We have to address water issues. We have to address land use issues. Now, I've mostly been, involved in the induced seismicity issue. It's what I know about and where I can make my contribution. But all of these things are important. And I want to address, something that came up that Emily said. And about 2 years ago, I was asked to give a talk about unconventionals at an energy seminar, and my schedule got all confused, and I couldn't do it. And so I sent one of my graduate students, and he was fairly senior, and he really was articulate and knowledgeable, and he gave, I'm sure, a pretty good talk. But one of the questions from the audience was, what about the environmental impacts? And he was, so I've heard all this secondhand, of course, I wasn't there. He puzzled for a second, and then he said, well, there aren't any. And, he was almost run out of the room, and I realized that I was leading a double life. I was talking about disciplinary expertise, geomechanics, with my students and making them as absolutely good at what they do as I could. But I wasn't talking about sort of my other life, and that was, dealing with committees and the public on these kinds of issues. So we as professors do have a responsibility to make our students aware of what these larger issues are and to keep our disciplines in the context of broader scale issues and broader scale concerns. And along that same line, we at Stanford have now launched a natural gas initiative. I've agreed to direct it, and it goes from upstream to environmental, to the uses of natural gas, to economics, finance, regulatory issues, and it's just a remarkable thing to be learning new things from my colleagues in these many diverse fields. And there is so much to do. We are not in competition, with the Jackson School. We are not in competition with other leading universities. These are global scale problems that will take all the best minds at all the best institutions to address. So, with respect to my advice for the next 10 years for the Jackson School, strive for academic excellence, identify important societal questions, foster multidisciplinary approaches to solving these complex challenges. But you already know this, you're already working on it, and changing course is the last thing you should do. You're on exactly the right track, and I wish you great success in the future as you've had in the past. Thank you.
Well, that's 2 home runs from the keynote speakers, so thank you, George, and thank you, Mark. I think one of the things that really resonated with me about having leaders, and Bob Carell is certainly a hero to many of us from the National Science Foundation, to turn problems into solutions. I think that's one of our grand challenges as leaders, so thank you for challenging us. So next I'd like to add some of the panelists to give each of the panelists to give their perspective. So I'm going to ask each of them to come up and give a little bit of again, their perspective on things, and we'll go in the order that they're said. So first, we'll bring up Sergey Fromel.
So how important is geophysics for the Jackson School? So I'm going to offer you one measure. Right now, many of us are looking through the list of applications to the graduate school. So out of about 520 applications, about 110 list geophysics and seismology as their primary area of interest out of a long list of themes and disciplines. So this makes it the most popular area, followed by energy and then sedimentology and stratigraphy and so on. If we count applications that list geophysics and seismology as one of their interest areas, not necessarily the primary one, it's almost half of them, so about 45%. So this is one measure that tells us that geophysics might be important for the school, but of course we can use other measures, and we can also reject all those students and send them to Stanford. So how important is geophysics in the real world? This chart appears in a recent publication, so I will show you. It's kind of hard to see it from the back, but I will show you the reference in the next slide. What we try to do here is map different sources of information about the subsurface, so the upper crust, on two scales, horizontal interpretability and vertical interpretability. And the scales are logarithmic. So in one corner we have core samples, and they actually cover a wide range of scales on the logarithmic scale. And then we have other sources of information. There are outcrop analogs, well logs of different kinds, and in the opposite corner, in the top right corner, there is 3D seismic, the most popular geophysics method. So it covers the range of tens of meters to thousands of meters. And the most disturbing about this chart is the realization of the gaps that we have between different sources of information in scale. And I believe this is right now the biggest problem in applied geophysics, or a grand challenge if you want. How can we extend the scales of interpretability for geophysical data so that it connects with other sources of information and we can build a common picture of the subsurface? So the paper is this one. It involves two Jackson School alumni, Will Burnett and Rishi Bansal. They are now at ExxonMobil. And this was a study we did with them a couple of years ago in Piance Basin. And the computation we did for the study was very interesting but very strange, because we took seismic reflection data, we enhanced reflections, which is our primary source of information, and then we threw them away. So we looked at what was left after you get rid of your primary signal, and what was left behind were diffractions, diffracted waves that originate at small subsurface features. And these were the source of very important information that goes beyond the usual seismic scale. And this is a more recent example published this month. It's a work of Dmitry Merzlikin, a PhD student, in collaboration with colleagues from Australia. So this is another unconventional tight gas reservoir, and we see a comparison of the conventional image from seismic reflections and a diffraction image, and an amazing level of details we can see using diffractions. So seismic diffraction imaging is an exciting new way of looking into the Earth. It originated here, so it's now changing the world of applied geophysics, but it's only a small step on a long road that we need to travel in this direction. Thank you.
Thank you, Sergey. So next I'd like to have Liz Logan come up and give a bit of her perspective.
Terry asked us to talk about our contribution to geophysics, which, just having defended in October, felt presumptuous of me, but I'll just talk about something that motivated me to start. This is a little video clip. Emily Cooper-Dock's dad was a professor of mine at Columbia, and he came into the room, into class one day and said, "Oh, part of the Larsen had just exploded. It wasn't this part of the Larsen ice shelf. I study ice. The white stuff is ice, the black stuff is ocean." And the statement and the idea just sort of hit the room like a ton of bricks. So in my graduate work down here, I came down and wanted to understand the question of how do ice sheets lose mass? All the colored stuff is part of floating ice, and it holds back the ice that'll fall into the ocean and help global sea level rise. And then can we predict it? Can we predict near term how ice will retreat at the margins? Can we make a tool? So that was my goal, to contribute at least, was to make a tool that scientists who had lots of data could use to understand that data and see how the world is changing in relative close temporal term. So my workflow throughout school was take the data, develop a numerical model, and try and use it to predict something. So the top sort of left to right data model prediction part was a paper where we were looking at the retreat of a really fast-moving and quickly changing glacier in Antarctica. The bottom part is that same glacier with a more complicated model. So eventually we're trying to use this model to help predict and make something that's really going to interface and be important to humanity. So at least in terms of grand challenges, which it wasn't clear to me before Emily and I were talking what they were, development of tools, making them available for posterity, scientist posterity, and just making that freely available. So that was a part of my work here at the graduate school. Keep it short so we can move on.
Thank you, Liz. Next up, Don Blankenship.
Yeah, a little bit ago, as part of the strategic planning exercise, Terry gave me the challenge of gathering together the Institute's input to this. And two things. We had an energy group, climate dynamics group, a polar and planetary group, and a marine geosciences and tectonophysics. And all these things came in, and there were essentially two themes. One was the motivation was the baseline was habitability. What is the origin of life, stability of evolution, or the Earth is a place for a bunch of colonial hominids to continue to survive. And then the other was transitions, rapid transitions in space and time. And so that spanned everything. And so what we're going to show here is what we've managed to do. Jack Jackson did this. This is Reason. This is their radar for Europa assessment and sounding from its ocean to near surface. Remember, Europa is the moon of Jupiter with a global ocean and about 10 kilometers of ice sitting on top of it. The Jackson School, people don't know this, Jackson School is the lead institution for the lead instrument on the next Outer Planets planetary flagship mission. Arizona's not. Berkeley's not. MIT's not. We beat MIT, by the way. And we did that, and Jack Jackson did this. Now, how did we do this? It has to do with the Institute, actually. And habitability is the motivation. We want to know if there's life on Europa. The tool here is a radar. And a radar looks through ice, the transparency. That's already come up today. And so that's what we do at the Institute. But we don't do it in planets. We're not a planetary organization. We care about those processes. We care about ice. But what we're good at is understanding ice and actually understanding ice from a perspective relative to habitability. So this is what Jack, in about 2008, in 2005, when the Jackson School started cranking up, there became, an infrastructure fund that was available for doing things. And those problems that Liz was working on in Antarctica, that collapsing ice sheet, this is the profile that she was working on. The one over the right, that's a radar. You're looking through 3 kilometers of ice. Transparency again. And we said, well, let's make this available to the whole continent. We were doing it over short distances, a few hundred kilometers. And we put this airplane together that allowed us to do the entire continent of Antarctica. Okay, so we're doing radar over the continent, and then we're actually doing gravity to look under the ocean as well, because the bathymetry isn't known around Antarctica. So Jack did that, thanks. Okay, how did that get us to Europa? Well, there's a radar over there, and Europa's got 10 kilometers of ice, and that's 3 kilometers of ice. We're halfway there. So that gave us the background to tell the planetary community things they didn't understand. Rapid transitions. Liz had talked about the collapse of ice shelves. Turns out to be that's a dominant process on Europa, and we had wrote a sort of a cardinal paper on the collapse of the surface of Europa that gave us the credibility to propose to use our radar to get $150 million to go to Europa and ask the question of whether it's habitable. So that's that. Our motivation, why did the Institute get into this? And it's because of these big blue spots here in Antarctica. That white spot there is about the size of Texas, and the blue spots are 2 times the size of Texas. And those are the parts of Antarctica that are below sea level and unstable. In other words, a rapid transition. It's nonlinear dynamics, the unstable marine ice sheets. The whole world is working on the left-hand blue spot. No one was working on the right-hand blue spot. So the Institute said, let's take that airplane and do the right-hand blue spot. They were unexplored. And that's very, very, very big news these days, because there's 20 meters of potential sea level in the right-hand blue spot and 3 meters in the left-hand blue spot. Okay, and it looks like the right-hand blue spot is starting to respond to warming of the oceans. So that's about it. And where are we going? NSF isn't big enough. We need the whole planet working on this problem. And so what we're doing now, the upper right-hand corner is the airplane we put together for China, doing the same thing. The lower airplane is the one we're doing with Australia. So we have Australia and France working in the various boxes there. And then we've just migrated these instruments to the helicopters that Korea and Sweden are flying for the problem that in 3 days we will be flying over Liz's cracks on Thwaites Glacier with a UTIC helicopter, operated by a Kiwi, financed by Korea, and supported by Sweden. And so that's where we are. That's what the Institute does. There's a drone there. We also have the vision of getting people out of these airplanes and automating a lot of this work because we're going to have to monitor these things. And so Australia is supporting us with that, and we have an MRI in with NSF. So the U.S. is coming back in to help us perhaps do that. So that's the sort of thing we're trying to do, and if it wasn't for Jack, we wouldn't be here. Thanks.
Thank you, Don. Next, Laura Wallace.
So I'm going to talk a bit about something that I think is a grand challenge in geophysics, and really understanding plate boundary processes, in particular subduction plate boundary processes. And I think this is one of the most compelling geophysical puzzles of our time, in large part due to some really surprising discoveries that have happened at these subduction plate boundaries in the last 10 to 15 years. The picture on the left is just showing slip on the fault where the magnitude 9 earthquake occurred off of northern Japan in 2011. This is Japanese researchers realized that earthquake actually involved incredibly large slip right out near the trench, right out near the seafloor, over 50 meters. And this was a complete shock to all of us who've been working on subduction zones, and really caused us to reevaluate how we think about how these things work. And then the other discovery that's been incredibly exciting in the last 10 to 15 years is the discovery of slow slip events at subduction zones and also at other types of plate boundaries around the world. But these were really only discovered because of the advent of continuously operating GPS networks at plate boundaries where we can see these slow deformation events happen. And what a slow slip event is it's similar to an earthquake in that it involves more rapid than normal movement along a fault. Except an earthquake takes seconds to occur, a slow slip event takes weeks to years to occur. So we had no idea that faults actually did this kind of thing, that there's this whole family and whole spectrum of different types of fault slip behaviors between the two more traditional end members of earthquake slip and steady creep. So this has made us realize we have a lot of questions we still need to answer about these things, and these are really societally compelling questions because subduction zones produce the largest earthquakes and the most devastating tsunamis on Earth. And geophysicists at UTIC have had a long history of contributing quite a lot to understanding these types of plate boundaries, particularly in the offshore environments. And also I would say that a lot of geologists and also geochemists in the Jackson School have contributed to these problems as well. I want to focus in on a problem because this is something that I've been working on that is kind of a concrete example to me of one of the benefits of being here at the Jackson School. Before I arrived here 4 years ago, and before I arrived here, my experience had largely been in using land-based GPS to measure tectonic deformation. But one of the big sort of frontiers in my field of geodesy is actually to be able to do this in the offshore environment. And this has been a really difficult nut to crack. And when I came here, we put in an NSF proposal with collaborators in the US and Japan to do a study offshore New Zealand at the Hikurangi subduction zone to try and investigate deformation due to very shallow slow slip occurring out near the trench at the plate boundary. This is something that had never been done before. And part of the reason that I had the courage to kind of jump into something new was because of the expertise that exists here. We have a great marine technician at UTIG, Anatoly Mironov, who's an expert in seafloor instrumentation. We built several of the instruments that we used in this experiment. What these instruments are seafloor pressure recorders that essentially measure pressure due to the overlying water column and can measure if the seafloor, you can tell if the seafloor is going up, you get a pressure decrease, or if it goes down, you get a pressure increase. So we sort of got NSF to take a risk on this to see if this would work, to look at offshore deformation. And sure enough, it actually worked, I think, about 100 times better than any of us expected it to work. We just got our instruments back in June of last year. We had a big slow slip event beneath this network. We recorded pressure changes related to deformation of the seafloor, vertical movement of the seafloor during slow slip event on the order of 1.5 to 5.5 centimeters. And we were able to get an unprecedented sort of detailed view of deformation of the seafloor during one of these slow slip events. And we found that the slow slip actually went right up almost to the trench, which had never been documented before. So this gives us a better understanding of the range of sort of physical environments that these slow slip processes can occur in, and also the nature of deformation and fault processes out near the trench where tsunamis are generated. So going ahead, I just want to make a couple comments just from my perspective as somebody who's only been here for about 4 years. But I think going ahead, we really need to maintain and really enhance this unique ability that we have to leverage the resources at the Jackson School, both the financial resources and the personnel resources, to pursue really high-risk, high-reward science that's at the cutting edge of geophysical problems. I think we need to really increase our presence in some of these critical areas of solid earth geophysics. Some recent hires and also recent instrumentation capability development, I think, will push that forward. And also, I think, encourage really interdisciplinary research that already exists at UTIG and across the Jackson School, but also tap new opportunities for more cross-unit collaborations. Like, for example, there's a lot of people looking at subduction problems in the department from geophysical and geochemical perspectives that I think would dovetail really nicely with some of the more geophysical questions we're asking at UTIG. So.
Thank you, Laura. In our remaining time, I'd like to get some questions going. I'll start with that, but I first have to comment that I didn't know there was someone who could talk faster than I did, but that was pretty good. Pretty good. So I guess the questions to the panel will go down the line to address this, if you will. Breakthroughs often come by disruptive technologies. Disruptive technologies like your iPhone, which is now a computer in your hand. So in geophysics, what do you see as the technologies that are needed to make some of these breakthroughs happen? And let's not talk about funding. So Mark, any thoughts of? No. Should go green.
Okay. I'll refer to two past examples. One is the slow slip events that Laura just described. I was at a meeting, an IRIS meeting, in which the data were presented really for the first time that demonstrated what had been interpreted as noise on seismometers came in bursts that correlated with unusual geodetic signals seen on GPS instruments. And the two things came together in almost an amazing coincidence. And, everybody, there's about 100 people in the audience, were just sort of dumbstruck to learn of this, this major discovery that had completely overlooked. The fact that there was a family of types of slip on these subduction zones and changed our entire perspective. And it came from correlating two different sources of noise by two different groups of scientists in two different, kinds of geophysics in two different parts of the world. And, it just sort of happens. And the second example is what was hypothesized by my colleague John Claerbout 30 years ago, and that is that one can do interferometry with noise, seismic noise. And as Sergey knows far more about than I do, but now it in fact is analyzing the noise in seismograms, is giving us detailed information on the shear wave velocity of places like, in seismic areas where you really want a detailed image of the shear wave velocity in the near surface because it amplifies seismic waves. And we know when an earthquake occurs, damage is very heterogeneous because of what are called, basically local effects, local soil effects. And in the upper few hundred meters, those variations are extremely important, need to be mapped, need to be recognized. And that came from also studying a different kind of noise. And so I don't have I can't tell you what we're going to destruct in the future and what understanding will come, but we don't have to look very far back in the past. We're talking about the last 10 years of really beautiful new science, beautiful new understanding that can be applied to very important problems coming from very odd areas that had never been looked at before by imaginative and hardworking scientists.
Thank you, Mark. Sergey?
So I would like to think that big breakthroughs happen through the kind of research that I do in computational data analysis. But if I look in the past, I have to admit that some of the breakthroughs that we witnessed came from just collecting more data. So simple rule that with more data and more interesting data comes more information works. So for interferometry that Mark mentioned, I think there is an exciting development in seismology with simply collecting denser recordings, so what we call the complete wavefield. So it's very exciting for us in reflection seismology because now we can try to use some of our techniques on passive earthquake type data. And similarly, previous advances like 3D seismic, multi-azimuth seismic, there was a lot of new data analysis, but they came also from collecting more and richer data.
Thank you, Sergey. Liz? Just turn your phone.
Hello. This one seems less sensitive. Hello. Yeah, just to piggyback on what Mark and Sergey said, certainly, noise, accidental data, lots of data, these are all good things for disruptive technology. I was sitting behind one of the speakers at graduation this fall, and she said big data was going to be a big deal going forward, and that's great. Big data is a buzzword. Sometimes I don't think I know what that means when people use it, but in terms of big data, the University of Texas has at its disposal the #1 supercomputer out of a university in the world, Stampede, and we can partner with that. That's science that you can get a lot of bang for your science buck. And so, yeah, I don't know if you can predict disruptive science, but certainly you can forage ahead with lots of data and really leverage it within your computer models and inverse techniques to make the most use of what you get. And just keep going down the line of what Sergey and Mark had suggested.
Thank you, Liz. Just turn your Don.
Yeah, I guess I'll pick that up and go a little bit, test, gotcha. Go a little bit farther, I'd say smart data. That we have these enormous capacities to collect data right now. We have these enormous capacities to model, but it doesn't take much to create a sort of an interconnected, interdisciplinary forward problem that defeats the machines. And so we've got to do diagnostic models and predictive models. And so the diagnostic models are going to take good inverse problems. The disciplines have been great at generating forward models, but when we couple those forward models, we have to go collect data to figure out which process is dominating. And so it needs to be smart data. So you can use the inverse models to look at uncertainties and sensitivities, and that's within the scope of the big machines. We're not overtaxing them. And so to direct our observations, now that's for diagnostics, to understand how things work. As soon as we understand how things work, then we want to predict. Climate change comes into play right away. But that's a different kind of data. That's monitoring data. We need to go out and we understand how things are working, and we're looking for change. We go from a rapid transition in space to a rapid transition in time. And so to use those models to look at that, you have to be coupled to routine observations. We think about the cryosphere because the cryosphere is changing a lot. And that's why we're trying to go into autonomous monitoring. We need to really, really, really watch these things continuously, not just go measure it once to verify that our process works and that our discipline will reward us for it. So we need to use that process to predict. And we need to collect data and intelligently. We can't get it everywhere. So smart data and heading towards predictive modeling.
Thank you, Don. Laura?
Okay, there we go. I've tried not to talk so fast. Yeah, I mean, I totally agree with the a lot of the things everybody said here, and so I don't really have a whole lot left to add, but I mean, again, I just kind of emphasizing, you know, kind of thinking in terms of high risk, high reward, and you know, trying new things that, you know, aren't necessarily guaranteed to work. But then also in our environment, you know, we're constantly pressured to get more and more grants funded and collect more and more data, and I see all the time people run out of time to really exploit their data sets, and I think there's a lot of existing data out there that is poised to kind of create these new exciting discoveries. And you know, I think, you know, if resources can be made available to people to be able to actually work that stuff without having to get the next thing, this could help.
Great. Thank you, Laura. So this is a question from George, and I think it's actually interesting because now I need to go back to my science philosophy class. Discovery, like Gruden would refer to the absence of heat flow in the San Andreas as the empty chair. And he would refer to the presence of seismic noise, i.e. slow slip, as the uninvited guest. So so I think they're more of a comment from George, but you're tweaking my brain on past time. That's really good. So I think the other question was similar to what we've had before. I guess that's one last question is, the first panel had 3 females on it. This panel has 2 females on it, but I look in the senior levels of geophysics, I don't see the same ratio. So what are the challenges for gender and diversity that we have in geophysics, and how can we meet that challenge?
All right, I'll bite. Paid paternity and maternity leave, and lots of it. That's a guess. I have no idea.
That's good. But
I think it's going to change because, I mean, you look at geology graduate programs in a lot of schools. You do see a higher ratio of women that do at more senior levels. So I think that's just going to take time in some ways, and we need to be patient, but I don't think we can be complacent either. I think that some of the things Liz was talking about, but then also being actively aware of this and hiring decisions and things.
About 12, 15 years ago, when I was chairman of the geophysics department, I did a survey of recent graduates, and one of the purposes of the survey was to really find why women weren't entering the professoriate. There were plenty of women graduate students. They did just as well as the men, but they didn't become geophysics professors. And so I thought the best people to answer that question wasn't my 12 other male colleagues in the department. We asked, and it was about 10 years of graduates that could be accessed online. And what overwhelmingly came back was the lack of women faculty who could be role models and mentors and show them that there was a path and a career for women as professors. And I'm very happy to say we have four women professors in geophysics right now, and you just have to start and you have to work hard at it. But I think the real key and it's no different in this than many other similar examples is you have to have women as part of the game, and then young women coming along will see their role in an appropriate context.
thank you. Okay, I think at that point we should wrap this up. I want to thank the speakers and the panelists again for a fantastic panel. Thank you very much.